A planetary scientist stood up at a conference in Paris this month and presented a result that sounds, at first, like the most reassuring thing you have ever heard. He and his colleagues had run more than 1,000 simulations of how our solar system formed. And unlike almost every model built in the last 30 years, they did it without telling the computer what the answer was supposed to be. No assumptions about where the planets should end up. No fitting the model to the sky we already see. Random starting conditions, and then physics, left alone, allowed to run. And a planet kept appearing. At 1 astronomical unit, the exact distance Earth orbits from the Sun, a world of roughly Earth's size emerged, over and over, as the ordinary outcome. Not a rare result, not a lucky roll, a natural consequence of the process. The researchers' own summary was blunt. There is no reason to think Earth is a fluke. That should be comforting. It is not, and the reason it is not has nothing to do with the model being wrong. Because in the same set of simulations, the planet next door, Venus, showed up only about 28% of the time. Your neighbor is a coin toss. You are not. And if Earth is not an accident, if a world like this one is what a star system produces when nothing special happens, then the oldest and most disturbing question in astronomy stops being a question about probability. It becomes a question about what happened to everyone else. To understand why this result matters, you have to understand what was wrong with the way we did it before. Modeling planet formation is a specific kind of hard. You cannot run the experiment. You have one solar system, it took tens of millions of years to assemble, and it finished 4.5 billion years before anyone was around to watch. So you simulate. You start with a protoplanetary disk, the flattened cloud of gas and dust left over around a young star, and you populate it with the raw material, planetesimals, kilometer-scale bodies, and planetary embryos, larger objects on their way to becoming planets. Then you let gravity work, over millions of simulated years, and watch what collides, what merges, and what gets thrown out. That is the method, and it has been refined for 3 decades. But there was a problem baked into it from the start, and it is the kind of problem that is very easy to not notice when everyone is doing it. We already knew the answer. We know there are 4 rocky planets. We know roughly where they sit. We know Jupiter is enormous and out beyond the asteroid belt. And when you build a model of how a system formed, and you already know what that system looks like today, it is nearly impossible to avoid steering, choosing starting conditions, tuning parameters, selecting the runs that produce something resembling home. The scientist behind this new work, Nader Hagheipur, of the University of Hawaii at Manoa, put the problem plainly. After roughly 30 years of doing terrestrial planet formation one particular way, the field reached a point where the limitations of that approach could not be pushed any further. That is a serious thing for a researcher to say about his own field, because a model tuned to reproduce a known outcome tells you that the outcome is possible. It cannot tell you whether the outcome is likely, and likely is the entire question. Whether Earth is common or Earth is a miracle is not a detail. It is the thing underneath every other question we ask about life in the universe. So they threw out the starting point. The approach in this new work is to make no assumptions about the planetary architecture we are familiar with. Instead of beginning with conditions chosen to produce our solar system, the simulations begin from many completely random starting points and let the physics drive the evolution to whatever it produces. Nobody knows what the real starting point was. Nobody knows how objects of different sizes were actually distributed in the original disk around the young sun. That information is gone. It was destroyed by the process itself. So, rather than guess and then defend the guess, they went back to the beginning and let the physics take over. There is one structural finding worth pulling out, because it is the technical heart of the paper. The most viable environment for forming habitable planets, one that emerges organically rather than being imposed by assumption, is a protoplanetary disk in which the solid material is not evenly spread. A non-uniform disk, Lumpy. That sounds minor. It is not. A smooth, evenly distributed disk is the simple case, the one that is easy to set up and easy to reason about. What the simulations indicate is that the messy version, clumps, gaps, uneven concentrations of rock, is the one that reliably produces worlds like ours. Which is a satisfying result, because messy is also what we actually observe. Real disks around real young stars, imaged by modern telescopes, are full of rings, gaps, and asymmetries. And then there is the reason this study could be done at all, which is not astronomy. It is hardware. Simulations of this type used to take 6 to 8 months to run. The same work can now be done in 6 to 8 weeks, on current laptops. Sit with that for a second. The bottleneck on one of the largest questions in science was, until very recently, that the arithmetic took most of a year. Now a researcher can run 1,000 universes on a machine you could carry through an airport. That is why the field can suddenly stop tuning and start sampling. So they ran it. More than 1,000 simulations of the late stage of rocky planet formation, across a variety of distributions of planetesimals and embryos. And here is what came out. Earth, at 1 astronomical unit, is a natural outcome of the evolution of our solar system. Not one run in 1,000, not a statistical curiosity buried in the tail. The ordinary result. Give a young star a lumpy disk of rock, and let gravity do what gravity does for a few tens of millions of years. And a planet of about this size, at about this distance, is what tends to be there when the dust settles. Then Venus. Venus appears in about 28% of the runs and holds its orbit. Sometimes that orbit sits inside the habitable zone, sometimes just outside it. And Mars appears a number of times, as a small object in the neighborhood of where Mars actually is. 3 planets, 3 completely different confidence levels. If the idea that your own planet is the predictable part, and your neighbors are not, is the kind of thing that keeps you watching, subscribe. This channel reads the papers. Now, the 28%. 28% is the number I cannot stop thinking about, and almost nobody covering this study has said why. Venus is nearly Earth's twin. Almost the same size, almost the same mass. Made of the same material, formed from the same disk, at a distance that is not enormously different in cosmic terms. And in these simulations it shows up barely more than a quarter of the time, while Earth shows up as a matter of course. The explanation is the sentence in this research that does the most damage to our intuitions. Even a small variation in the initial conditions can have an enormous impact on the final product of a given system. That is chaos, in the technical sense. Not randomness, chaos. A system where tiny differences in the starting state produce wildly divergent outcomes, deterministically, with no dice involved anywhere. And it means the solar system has 2 kinds of features. There are robust features, outcomes so strongly favored by the physics that they show up almost regardless of how you start. A rocky planet at 1 AU is apparently one of these. And there are contingent features, outcomes that depend on details that were erased 4.5 billion years ago. Whether a particular body ends up in a particular place, whether 2 embryos merge or scatter, whether the third rock has a twin, which flips the usual framing entirely. The version of this story you have heard your whole life is that Earth is precious because it is improbable. A knife edge, a lucky accident, a 1 in a billion arrangement. This work suggests something else. Earth is not the improbable part. Earth is the reliable part. It is everything around Earth that is up for grabs. Now follow the logic out, because this is where a comforting headline turns into something else. Haghayapor's own extension of the result is that given how common Earth-sized planets, including small super-Earths, appear to be in the habitable zones of sun-like stars, it is entirely logical to consider that Earth-type life is common. Hold that against the number of stars. Our galaxy contains on the order of 100 billion of them. A substantial fraction are broadly sun-like. Exoplanet surveys over the past 3 decades have found that planets are not rare accessories to stars. They are standard equipment. Add this result. Rocky worlds in the temperate zone are a natural output of the process, not a fluke. Multiply it out, and the galaxy should be full of Earths. Not dozens, not thousands. An enormous number, most of them far older than ours, because the galaxy was making stars for billions of years before the sun existed. And the sky is silent. That is the Fermi paradox, and this is precisely the kind of finding that sharpens it into something uncomfortable. Because there were always two ways out of that silence. The first was that Earth is a freak. That the chain of coincidences required to make a world like this is so long that we are effectively alone, and silence is exactly what you would expect. The second is that something happens to civilizations. This research does not prove anything about either, but it takes weight off the first explanation and puts it on the second. If the hard part is not making the planet, then the hard part is somewhere further along the chain, in the origin of life, in the jump to complexity, in intelligence, in technology, or in whatever comes after technology. And every one of those is in front of us, or was very recently. The reassuring headline is that Earth is no fluke. The unreassuring implication is that if we are not rare, then our being alone in the data requires an explanation that is not about luck. Now I have to do the honest part, because the coverage of this is already outrunning the evidence. This work was presented as a paper at a conference. That is a normal and important stage of science. It is how results get shown to the field and argued about. But it is not the same as a fully peer-reviewed publication that has survived formal review. It is also one team's models. Other groups have their own approaches, and planet formation is a field with real disagreements. And there is a much larger caveat that applies to every simulation ever run. A model is not an observation. These are calculations about how gravity moves rock over millions of years. They are constrained by physics, but they are still a description of a process nobody has watched. The field also has a history of this exact humility being necessary. For years, standard simulations had what was known as the Mars problem. They kept producing a Mars far too large, sometimes several times its real mass. That is not a small discrepancy. It is a model confidently generating a solar system that is not the one we live in, and it took substantial new thinking to address. So when the new models produce Mars as a small object roughly where Mars is, that is genuinely notable. And it is also exactly the kind of match that should make you ask how many runs were examined and what counts as a match. None of this is a reason to dismiss the result. It is a reason to hold it at the right pressure. Let that land for a moment. Because the difference between what this study says and what the internet will say it says is going to be enormous, and it is measurable in one word. The study says Earth's formation is a natural outcome, likely, unsurprising, expected from the physics. It does not say Earth was designed, intended, or inevitable in the way people will want it to mean. Those are not the same claim, and the gap between them is where every bad version of this video is going to live. So how would we ever check? Not with more simulation. You cannot settle a question about how common life is by running better calculations about rocks. At some point you have to go and look. And that is exactly where this runs into the wall. Haghayipur is direct about it. Finding life around other stars is extremely complicated, and our technology is not at that level. We can detect planets. We are good at it now, thousands of them, by watching stars dim as a planet passes in front, or wobble as a planet pulls on them. Detecting life is a different order of problem. It means measuring the composition of an atmosphere on a small rocky world, tens of trillions of miles away, in the overwhelming glare of its own star, and then arguing about whether a particular combination of gases requires biology or just unusual chemistry. That last argument is the hard one, and it is not hypothetical. The field has already had public disputes about exactly this kind of tentative signal, where the same data supported both a biological reading and an entirely boring one. So the value of work like this is not that it answers the question. It is that it tells us what to look for and how surprised to be. Understanding what physical processes make a planet like Earth and how it becomes habitable is what you need before you can judge whether a distant world is a candidate or a curiosity. We are building the expectations now, so that when the instruments finally arrive, we know what we are looking at. There is a photograph from 1972, taken by an astronaut on the last crewed mission to leave low Earth orbit, of the whole planet lit from behind the camera. Blue, white, fully illuminated, alone in black. For 50 years that image has been used to make one argument: look how fragile, look how singular, look how improbable. This research suggests a different caption: not a miracle that barely happened. A thing that the universe does, reliably, in disks of lumpy rock around ordinary stars, whenever gravity is left alone long enough. Every photograph you have ever seen of Earth from space is accurate. It really is that blue. It really is alone in the frame. The picture just stops at the edge of our own system. And what is past that edge? 100 billion stars, standard-issue rocky planets at temperate distances, and not one confirmed signal from any of them, is the part that decides whether being unremarkable is good news or the worst news we have ever had. So here is what I want to know from you. If Earth turns out to be the ordinary output of ordinary physics, what do you think the silence means? Is the hard step still ahead of us, or is it behind us, in the origin of life itself, and everything since has been the easy part? Tell me where you think the filter is, in the comments. I read every one. And, if this one got to you, the next video is about the one step in that chain that nobody can explain at all, and why the scientist in this study said we may never know how it happened. Watch it before you decide we are alone.